Good. That'll be fine. Okay, I like to think of nonlinear optics as a kind of optical alchemy. In the way that the old alchemists tried to turn one element into another, combine a couple elements to make a new element, here in nonlinear optics we combine a bunch of colors to make new colors. Okay, and you know, there are a number of references on this. Nonlinear optics is a big field, and I've just listed a few books here. I'm not going to give any references to papers or review articles during the talk, except maybe for one. But if you have any, if you're after a particular reference on a particular subject, you can grab me after the talk, and I'll try to point you in the right direction. These are some books that are all very good, cover different aspects of nonlinear optics. I think in terms of getting a sense of the spirit of the field, you might look at Bob Boyd's book on nonlinear optics. It's my only concern with it is that it's not so much focused on condensed matter, but and Bob never doesn't take all my suggestions as to what he should include in the next edition. But nonetheless, it's a very good overview of the subjects, and it'll give you a bit of certainly give you the spirit of the subject. Okay, so I'm going to go through a few topics in nonlinear optics. I'm obviously not going to cover all of nonlinear optics, but let's get started. I want to start with susceptibilities and begin with something you all learned in second year. Okay, I'm talking phenomenologically now about a polarization that's related with a susceptibility to an electric field. But in nonlinear optics, we understand this as just the first term in a kind of series expansion, where we involve higher powers of the electric field, and they're responsible for the nonlinear effects. Now, I'm a bit sketchy here. Of course, everything depends on position, and usually, or in what's called the long wavelength approximation, one assumes that if you're looking at the polarization at position R, it's only the electric field at position R and the square of the electric field and so on at that position that are going to be important. Okay, so this is in nonlinear optics sometimes called the long wavelength approximation. Near the end, I'll talk about some cases where one has to go beyond this. Okay. But I'll leave off the R's just to save a bit of space, okay? Now, of course, we have to remember that polarization is a vector and the electric field is a vector, so the relations that are involved here are tensors, okay? And I'll use the usual notation that if you see a repeated index, your Cartesian index, you're supposed to sum over it, okay? And this second one here, chi2, vanishes if the medium has center of inversion symmetry. Okay? So there's going to be restrictions on what kind of materials exhibit chi2. Gallium arsenide does, silicon does not, for example. Okay? It's also a little bit more complicated than this because we generally have a number of frequencies that are involved, and these susceptibilities really depend on the frequencies. That's maybe not surprising, you know that from linear response. The dielectric constant, or the susceptibility, is a function of frequency. The same thing happens in nonlinear optics, but because we have higher powers of the electric field, we're going to get combinations of frequencies that appear and that arise in the description. Okay? And that leads to this kind of notation, which is the first and one of the first annoying issues in nonlinear optics is this kind of cluttered notation. But you can see what's going on. I don't think I can. No, this doesn't work. I can't point to anything, but that's okay. There's a number of frequencies here. 3 of them, for example, in the chi3 term. Okay, and they're denoted here, and then the semicolon, and before this is the negative of the sum of those frequencies. Now you say, well, that's a really annoying thing to do. Why do you do that? Okay? And the reason is that in certain approximations, there are certain, there are certain, bottom one. Okay, yeah. In certain approximations, there are certain symmetry conditions that hold when you flip the Cartesian components and the frequencies when you write them in this way. Okay, so you will find in the literature expressions like this. Now, Unfortunately, there's not consistency in the literature. You will find something like this, for example, for this chi2, but the same thing is sometimes written this way, and you see what people have done. They've moved these forward and put this back and forgotten about the minus sign and so on. And sometimes people just, forget about the sum and say, well, it's sort of obvious if you add these two, you're going to get that. Okay, so sometimes you'll see things written this way. All these notations, and in fact more, are common in the literature, I'm afraid. Okay. But I'm going to more or less use this one, but what I normally do when I think about these things is I just forget about, unless I really need it, I forget about this first thing before the semicolon. So I think in my mind of just this. Okay. So then here you see, for example, for chi3, it's the 3 frequencies that appear here, and then that generates a polarization at the sum of those frequencies. Okay. Now, you might say, well, okay, how is one going to calculate that? And there's a number of different strategies. Suppose I wanted to calculate chi1 or chi2 or chi3 and so on. Okay. Well, you can certainly make simple models, and often that's good enough. Okay? You just make a model where you say, well, I have some molecules, and there's dipole moments, and they respond in a linear and nonlinear way to the electric field, and from that, I can build a kind of phenomenological model. And in some cases, that's fine. Okay? If you want to be a little bit more sophisticated, then, well, especially since we're in the long wavelength limit, J is just dp dt. Okay? So if I wanted to calculate that P, I could calculate J, and you could just go to a minimal coupling Hamiltonian, write down the problem, and then do linear response, nonlinear response, and so on, and calculate chi1, chi2, and chi3 by calculating the current density and then relating the polarization to that. Okay? And there's another strategy that goes back to Adams and Blount that's been talked about earlier in the summer school here, where you use an expression for the polarization in terms of these complicated things, right? These are the non-abelian Berry connections and so on, okay? And you can use this and then calculate the susceptibility that way. So all these strategies have and are being used, okay, at different levels of sophistication. Band structure calculations of nonlinear response coefficients have been done using the second two, okay? And there's a fairly large literature on that. Okay, everybody with me? I should stop occasionally and ask for questions. Any questions or comments from the experts? No? No, well, in this talk, pretty much insulators, yeah. Okay. In the second talk, I'll mention metals a bit. Yes?
Yeah, the length gauge, if you know nothing about what gauge could be better for some reasons?
In terms of convergence, well, the problem with the minimal coupling Hamiltonian is you get terms that look as if they're going to diverge. And they don't because there are certain sum rules. And you have to identify those sum rules. Okay? But if you can identify those sum rules, it's absolutely no problem. Okay? But the sum rules get harder and harder to identify as you go to higher and higher susceptibilities. Okay? You don't have that problem in the if you use the Adams and Blount strategy, okay, because problems don't arise. Okay. On the other hand, if you want to go beyond the long wavelength limit and worry about the variation a little bit of the electric field over the unit cell, there's no simple way to do that with the Adams and Blount treatment. In my second talk today, I'll talk about a way to do that. But you can always do minimal coupling, do it that way, but then you have to worry about false divergences or sum rules that you have to find to show that some terms look divergent, but they're really not. Okay, let me talk about then let's begin and talk about these sort of chi2 effects. Okay? And the first effect I want to talk about is second harmonic generation. Okay? So here you imagine you have a field at omega, and then that's going to allow you, if you have a chi2, it's going to allow you to generate a polarization that's going to oscillate at 2 omega. And if that polarization is oscillating at 2 omega, it's going to radiate light at 2 omega. So you're going to come in with light at omega, and you're going to get out some light at 2 omega. Okay? So if I think, for example, let's look at gallium arsenide. Okay? And imagine that I put on an electric field, an oscillating field at a certain frequency. And maybe when I start out with this electric field, let's say when the electric field is up here, the electrons between the gallium and arsenic are being driven towards the arsenic. And then a little bit later, they're going to be driven towards the gallium. Now those electrons would rather go towards the gallium than towards the arsenic, because the arsenic has more electrons around it already. So when I start to drive it in this way, I'm going to get a response that looks like this. They're not going to go so close to the arsenic as they do to the gallium. And this I can decompose into a fundamental polarization, a second harmonic polarization, and then a constant polarization. We'll talk a bit about that later. Okay? But there's these components, and this component now, this polarization, is going to be oscillating at twice the frequency you're sending in, and that's going to generate light at that frequency. Okay? So, for example, if I come in with light at about 347 at 694 nanometers, then I'm going to generate light at 2 omega, which corresponds to a wavelength of 347 nanometers. And in fact, these were the frequencies that were used in the first experiment that demonstrated second harmonic generation. And this is the paper that really started the field of nonlinear optics. Okay? So it's a paper it was published back in 1961 by Peter Franken and his group at University of Michigan. 62 years ago was the birth of nonlinear optics. Okay? And they went through the usual sort of thing, and they then showed their data. So this is basically a kind of wavelength scale here. Here's the light at omega. And it's a big blotch and so on. And here the arrow is pointing to the light at 2 omega. Now, problem is you don't see anything there. Okay? Now, of course, the light at 2 omega, well, much less intense than the light at omega. But the copy editors at PhysRev Letters thought that this was just a flaw in the photograph plate that was sent, and they airbrushed it out. Okay? So the copy editors of PhysRev Letters removed the experimental evidence for the effect that these people were claiming to show. Okay? Do we still have our colleague from Nature Physics here? I trust Nature Physics would do nothing like that. Okay? But this was done back in 1961 in PhysRev Letters. Okay? Now I'm using a laser pointer here in the red, but you've all seen, I'm sure, laser pointers that work in the green, very bright laser pointers. And these laser pointers, the green ones, in fact, work using second harmonic generation. Okay? There's a YAG crystal in here. There's a pump in the infrared at 1064 nanometers. Okay? And that the frequency gets doubled, the wavelength is cut in half, and out comes light at 532 nanometers. That's that bright green light that comes out of these green laser pointers. Okay? And of course, that all happens as the light propagates through this crystal. And I want to talk just a little bit about that, because let's imagine we have some second harmonic active medium like this. So polarization at 2 omega is chi2 times E of omega times E of omega. But of course, as this light at E of omega is going to propagate through the crystal, and so, well, this polarization is going to be a function of Z as we move along there. I'm sorry, I'm Canadian, so I say Z. The American speakers that you've heard say Z. Okay? So, Okay. Yeah. I tell you a joke. I had a visitor from Russia once, okay, and it was his first trip to Canada, and he said, you know, and he said, well, I'm just trying to understand things and so on. I mean, and you know how things are different between Canada and the United States and so on. And he said, do you spell civilization with an S or with a Z? And I said, we spell it with a Z, but we pronounce it Z. And his eyes lit up and he said, I understand Canada. Okay, so the electric field is going to come along, propagating e to the I k z here. So I'm going to get a polarization that has this e to the 2 I k z dependence. But of course, as I get it here and I get it here, I'm going to get radiation from these different bits of polarization. And that radiation at 2 omega is going to propagate at the k relevant for 2 omega that is going to involve the index at 2 omega, not the index at omega. So, in fact, I want these things to match up, and for them to so that I get a positive, I get a coherent positive superposition of these different contributions. So for constructive interference, I'm going to want k at 2 omega minus 2k of omega to be 0, and you can see that looks very hard because n at 2 omega in general is not going to equal n at omega. But experimentalists are clever people. They have different strategies. You can use birefringent crystals. So one of these indices might correspond to one axis and the other might correspond to another axis, and you can get this phase matching condition to work. There are other strategies that you can use that I won't go into, but for a lot of nonlinear processes, not all, but a lot of them, you have to worry about something like a phase matching condition to have that satisfied. Okay, so that's second harmonic generation, but yeah.
Can you get 3 halves omega and 1 half omega? So one will go up, the other will go down. It seems like, you know, energy is conserved and energy is conserved. Or if n of omega is something really.
Yeah.
But in principle, can you do that?
Can I make the ends?
So you split to omega.
Yeah.
This second harmonic. But can you go back? But of course you can go back, right? You can have single 2 omega frequency split into 2 omega.
Let me talk. That's coming. Okay, that's coming. Okay, let me just go through a bit more here, and then I'll get back to that point. Okay. Suppose I send in 2 frequencies now, say omega s and omega I. Well, I can certainly get second harmonic generation at omega I. So I can use this one twice. I can also get second harmonic generation at omega s, of course. I can also get what's called some frequency generation by, combining one of these with one of these, and I can get a polarization at omega I plus omega s. Okay, so that's generating a new frequency. But I could also, let's say now here I'm switching notation because I want to consider, for later reasons, I want to consider a strong pump here. And then I can get a polarization at omega p minus omega s by using the minus omega s component of this electric field. For obvious reasons, that's called difference frequency generation. So one can do all those things. Okay? But they're not all going on, in general, they're not all going on independently. For example, if I have some light coming in at omega, I can generate some light at 2 omega. But then, I think this is what you were mentioning, I can combine the light at 2 omega with a minus omega component, and that's going to give me light at omega. And that has to be, because I can't just generate light at 2 omega and not pay any price for it. That costs me energy. Okay? And that 2 omega light is really coming from the omega light. So this field will guarantee, it'll be out of phase with my original E of omega and take some energy out of the omega beam. So in general, I can get energy exchange between the beam at omega and the beam at 2 omega. Okay? Of course, I can get other things too. Once I have 2 omega and omega, well, one can go to town here. I can combine 2 omega, omega, and get 3 omega coming out. And so on and so on and so on. Okay? And in some cases, one has to worry about these higher order processes. But there is a whole class of processes where these following cases, because you generate very little of this light, these other processes are very weak, and you can forget about them to first approximation. And that's sometimes called the undepleted pump approximation. So when you hear undepleted or read undepleted pump approximation, that one's neglecting all those feedback processes that ensure energy conservation and generate new frequencies. Yes? What? The rectificate?
So for example, if you take the beam at 2 omega,
Yeah.
and you have one that goes this way and another one that goes this way,
Yes.
if you sum it, you will cancel out the frequency, right?
Yeah. You could do that even if they're going in the same direction. I'll get to that in a minute.
Uh-huh.
That's coming.
Uh-huh.
Okay. Okay, so let me just, yes.
How do you describe parametric down?
I'll get to that.
Okay.
That's coming. Okay. This is great. You guys are asking. Okay, it's
Thanks.
coming. Okay, let's do a little summary here. So for Chi2 effects, there's some frequency generation. That's not S-O-M-E, that's S-U-M, right? Some frequency generation. A special case of that is second harmonic generation. But other special cases are case here where I put on a DC field in addition to putting on an optical field at omega, and I generate light at omega. Okay? So this is sometimes called the Pockels effect or a linear electro-optic effect. And you see, it's like I'm introducing a new linear susceptibility, but here it's proportional to the DC field that I apply. Okay? And then, well, we talked about difference frequency generation. And one case of that is optical rectification. Okay? And here I combine field at omega and the field at minus omega to give something at 0. So here I produce a DC polarization. Okay? And you can see since E of omega is just E star of omega, this DC polarization is proportional to the intensity. Okay? And I can do that whether the beams are going in the same direction or different direction. Depends what I want to do. Okay? Okay. That's Chi2 effects. Let's talk about Chi3 effects. If I have something like silicon, I have a center of inversion symmetry. Okay? Unlike in gallium arsenide. So there's going to be no Chi2. It doesn't exist in silicon. But I can get a Chi3 effect. Chi3 effects occur in everything. They even occur in the vacuum. They occur in the vacuum because of virtual excitation of electron-positron pairs. Too small for us to measure, but in principle, even the vacuum has a Chi3. Okay? So here, for example, I can get third harmonic generation. Okay? Well, I'm going to get a polarization oscillating at 3 omega because I'm combining 3 fields at omega. Again, let's suppose I take 2 frequencies, a pump and a signal, let me call them. Okay? And then, well, any Chi3 process is really a 4-wave mixing process because I mix 3 fields and I generate a polarization and at another field that radiates at that. So there are 4 waves involved. But here's a 4-wave mixing process that comes up quite often. I take 2 omega p's and then a minus omega s. Okay? And I generate a field at 2 omega p minus omega s. Okay? And there are many others, right? Because I could take all kinds of combinations, mixing 3 fields and so on. Let me just sketch them out. Here's third harmonic generation, as we mentioned. Okay? Here's the 4-wave mixing one. I talked about. And this actually included in this, if you're dealing with molecules, is something called CARS, coherent anti-Stokes-Raman scattering. You can drive the vibration of a molecule. You can do this, you can drive a phonon in a crystal in the same way, okay, by coming in with a strong pump field and a signal field like this, okay? And you want omega p minus omega s to be the vibrational frequency you're trying to drive, okay? There's self-phase modulation. This is an interesting one, okay? So self-phase modulation, look, I've got omega, omega minus omega. So this is a p at omega that's proportional to E of omega times E of omega squared. So it's like the intensity is a new index of refraction. Okay? So here the intensity is modifying the index of refraction. Now, I want to use this to emphasize something, and that is, I've been talking about a perturbation expansion. You know, I've talked about chi1, chi2, chi3. Okay? But that doesn't mean that the propagation of the electromagnetic fields can be described in a perturbation way. You might think, well, you know, I have this term, it's small, so I solve Maxwell's equations without it. I take that as my 0th order approximation, then I go in and I find a little correction. Okay? And that, in general, will give you nonsense. Okay? Because with self-phase modulation, if I'm sending light, for example, down an optical fiber, I can get soliton propagation. That is not a simple perturbation of a linear pulse propagating down the crystal. Okay? So you have to distinguish between whether you're doing perturbation theory in the material response or you're doing perturbation theory in the structure of your electromagnetic fields. Okay? And in the condensed matter, it's usually justified to do the first, but there are many, many cases where it's not justified to do the second. And, well, here's cross-phase modulation. Okay, the intensity at omega 2, now you can use this to modify the index of refraction at omega 1. Okay? And this term also includes stimulated Raman scattering. It's included in that chi3 as well. Okay? And then finally, we have an electro-optic effect, sometimes called the Kerr effect. And here, you see I've got a DC field that I'm using twice. Okay? And that's going to give me then a change in, again, a change in the linear index at omega. Okay? So, there are many more of these processes. This is just a sort of an overview of some of them. Okay? Questions? Yeah.
So
if I try to do what you told me not to do,
Yes.
treat this as a perturbation in Maxwell equations, this cubic term, how would I know that I messed up? Would I get a secular, would this term be secular essentially?
Yeah,
it would grow with time?
Yeah, you would find that things would start to grow and it would be uncontrollable.
Right. So basically, because it's essentially resonant at omega, it'll just grow, the perturbation will grow.
Yeah, you'll get increasing
That's how I know I messed up.
contributions at omega. Yeah.
All right, thanks.
Yeah. Okay. Okay, I want to, any other questions? Everybody with me here? People, I can't tell whether you're, yes. Yeah.
Does the magnetic field of the light has any effect in nonlinear optics?
Yes, but not at the level I'm talking about here, because I'm talking about the long wavelength approximation. Okay? So that is, I'm neglecting the variation of the electric field, and that means I'm neglecting B because of Faraday's law. Okay? So if one goes beyond this, then magnetic effects do come in. I'll talk a little bit about that. I'll talk about at least one of those at the end of this talk, and I'm going to mention a bit of that in my second talk as well.
Thank you.
Any other comments, questions? Yeah.
So if I shoot in a photon, like or like if I shoot in like 1 billion photons, how many will actually undergo like, I don't know, second harmonic generation as opposed to just going through?
A very small number. I can't give you a number because we'd have to actually talk about the geometry and the material and so on and so on. But it's a small effect, okay? But you can do interesting things with it, which I'm going to talk about now, okay?
So small number, like 1% or like 1,000 of a...
Well, in the first experiment, it was much, much less than 1%, okay? But you can, there are now systems where you can pump things hard enough so that you do have to worry about pump depletion. So that means you can convert a significant number of your photons at omega to 2 omega. It's a bit unusual, but there are cases where you can do that.
Thanks.
Okay?
Happen to know the number for the green laser?
No, I don't. Sorry. Yeah. Okay. Let me talk about the one after the next topic is a little bit more related to things going on here, but I feel obliged to tell you a little bit about quantum nonlinear optics. Okay? And let me talk first about the regime where it comes in. So suppose I have a semiconductor or an insulator, and I come in with, say, 3 frequencies or some number of frequencies, but these frequencies are much, much less than the band gap. Okay? They're so much less than the band gap that even if I add them all up, I get an energy that's much less than the band gap. Okay? And if you're in that regime, then to good approximation, these chi2 and chi3, whatever these frequencies are, these things will be independent of the order of the Cartesian components. You can switch it at will. Okay? And they will all be real. And, of course, the index of refraction will also be real. Okay? So there will be no absorption process. This is important if you're doing quantum nonlinear optics, okay? Because you don't want to absorb photons. Okay? So suppose we're in this regime. Then you can do quantum nonlinear optics. But the way one talks about quantum nonlinear optics is different than the way one talks about classical nonlinear optics. And classical nonlinear optics is nonlinear polarizations, coupled mode equations as these fields propagate along and introduce envelope functions and so on. If you're doing quantum nonlinear optics, okay, you talk about Hamiltonians, raising and lowering operators, Wigner functions, and so on. It's a different language, okay? But it's not so hard to get used to the different language, and you can see parallels between what's going on. For example, here's some classical processes we talked about. We talked about difference frequency generation, and we talked about 4-wave mixing, okay? The quantum analogs of these are called spontaneous parametric down conversion and spontaneous 4-wave mixing. Okay? And you can see what's going on here. You know, this is exactly the same, except we're just putting the pump in. We're not putting in the seed. Okay? And likewise here, we're just putting the pump in. We're not putting in the seed. So here, spontaneously, we have photon fission. This photon at omega splits into 2 photons, one at omega s and one at omega I. And here it's a kind of photon reaction. We take 2 photons at omega p and we get one at omega s and one at omega I. And of course you know what's going on. Well, there's little quantum fluctuations here that are playing the role that in the classical case is played by the beam that you actually send in. Photons generated by these spontaneous processes, and you can sort of see that because the operators involved here are the same. You know, you're destroying a pump photon and you're creating a signal photon and an idler photon. Here, you destroy 2 pump photons and create a signal photon and an idler photon. Okay? And in fact, if you do these processes quantum mechanically, which you don't have to because a classical description is fine, but if you do, you find exactly the same operators involved. The photons generated in the spontaneous process are entangled. Okay? And if you pump very hard, you get a form of light that consists of many entangled pairs. It's called squeezed light, that I'm not going to talk about, but it's very important in quantum optics. And, one's interested in this for all kinds of reasons: quantum information processing, quantum simulation and computing, and fundamental tests of quantum mechanics. Okay? Now, in terms of quantum computing, I think I was told that here in San Sebastian there's an IBM institute that's working on developing quantum computers here. Have I got that right? Oh, okay. Well, okay. So the IBM strategy is based on superconducting systems. Other strategies people are looking at for quantum computers are cold atoms, cold ions, and so on. But there's also a photonic strategy that's based on the two spontaneous processes I talked about. There's a company in California called Sipe that's working very hard on that. There's a company in Canada, in Toronto, called Xanadu, which is also working on building a quantum computer. This is their lab. This is an optics lab. Notice the windows, you maybe can't see too well from the dive, but the windows are open. Light is pouring in. This is unusual for an optics lab, okay? Everything is at room temperature, okay? And what's going on is when one's using things like this, these ring resonators, okay? So I've got a channel waveguide here. This is maybe 10 microns in diameter, okay? Got a channel waveguide. Light can evanescently couple into this ring, okay? And it's like a photon hotel, right? The photons can check in. They can stay in the hotel for some time. Then they can check out, okay? But because if they're at a resonant frequency, and if they're at a resonant frequency, the intensity is going to be very high in this ring, and that will help you generate, your entangled photons, your squeeze states, okay? The best material for this at the moment is silicon nitride. Okay? But if any of you have an idea for how to use some topological material to generate a large chi-3, okay, in a regime where there's no absorption, if you have entangled photons and you absorb one of them, the other one is of no use to you. Okay, so we want no absorption. We want a large chi-3. Okay, if you can come up with that, come talk to me and we'll write a patent together. Okay, I'm joking. Okay, but if that would be an important contribution. Okay. Any questions on this? Yeah. I'm sorry, I couldn't. Silicon nitride. First of all, it's an insulator at telecom wavelengths where you want to use your pump because you have all kinds of technology ready. Okay, so one wants to work, at 1.5 microns for your pump. Okay, and therefore. And it's a chi-3 process, so they're also generating photons in the neighborhood of 1.5 microns, a little bit larger, a little bit smaller. So you want something where you can work very well in the telecom. So you want it to be transparent at 1.5 microns. You also want it to be transparent at twice that, or twice the frequency, half the wavelength, because you don't want to worry about two-photon absorption. Okay? Silicon would be wonderful, except there would be two-photon absorption there, okay? And you blow your material up, okay? If you have two-photon absorption of your pump, okay? So it's a wide bandgap semiconductor, transparent at 1.5 microns, at half that wavelength, and I think even at 4 times that wavelength, okay? So and people know how to make structures out of it with incredibly low losses. I'm talking dBs per meter in a nanostructure. Okay? When I was the age of the students here, okay, to get a dB, in 5 or 10 microns was a real achievement, okay? Now it's dBs per meter. Okay. Any other questions, comments? Yeah, Dave.
I guess in quantum processes, you have to worry about decoherence and other forms of.
Absolutely.
So is it mainly dominated by optical processes themselves that is the main problem, or are there like phonon scattering or other things you have to worry about?
In silicon nitride, the phonon scattering is also weak. That's another advantage of silicon nitride. The main problem you have to worry about is the scattering loss from the ring or from the channel waveguide, and that's why people have worked very hard at knocking that down, because in addition to a loss mechanism, that's a decoherence mechanism, which is a steeper price. Yeah. Yeah.
From my understanding of when the third order susceptibility becomes large, if we put a magnetic field and have Landau levels, isn't that a better way? Just a question.
Well, first of all, if you want to work at, first of all, there's an advantage to working at room temperature. And I'm not sure, and there's advantage to not having to have a 10 Tesla magnet as part of your quantum computer.
Yes.
So I don't want to discourage you from thinking in that direction, but I think that's the reason that people haven't focused on materials like that.
Okay. Thank you.
Yeah. Okay. Yes.
I can figure out why the electric field is strong on that surface. So at linear level.
Yeah.
At linear level, this is just a scattering problem, right? Like you're solving quantum mechanics. There is an incoming wave, transmitted wave, reflected wave.
No.
And it's coupled to that thing.
No, not quite. Okay? This is an all-pass structure. That
This
is
what's
all pass.
Uh-huh.
That is, in the absence of any scattering off the chip. Okay? Light comes in, it couples in here. When it couples out, it goes in this direction. There's no light going back.
Why is that?
Well, because the coupling in this region moves you from light here to light here, going in the same direction. And when it couples back out, it's light here going to light here in the same direction.
Okay, so in the electronic version of that, at the resonant, it would be actually perfectly reflecting, so it's very different.
And you can have photonic structures like this where it's perfectly reflecting as well. But this structure, these ring resonator structures, to good approximation, are all pass. And the nonlinear processes are enhanced just because you get a high concentration of the light in here.
Right, so high concentration, again, in the electronic version,
yes,
you would be sitting 1 over level width of seconds on that thing.
Yes.
Is it the same?
Oh, it's much longer. I mean, because the width of these the width of the resonant.
No, I mean level width, right? The modes on the circle, they have got to be broadened because of the coupling to the.
Very little.
So it sits very long then, right? So
it's resonance very long.
Very little.
Yeah, that's why you get the field
enhancement.
That's why you get the field enhancement. It's a high quality resonator. Qs here are, I think people have quoted Qs of 10 million.
All right. Okay. So don't flip this slide. Let me take a picture.
Okay. Okay, I will need some extra time because I'm being held back by this. Oh, okay. Okay. Okay, good. Now I want to talk about a connection between nonlinear optics and electronics. Okay. Or a number of different connections. Okay, now suppose now I start to increase the frequency of my light, and I get to a situation where I don't cross the band gap, but with 2 photons, I can cross the band gap. Okay? When you get in that regime, then this chi3, omega minus omega omega, acquires an imaginary part. Okay? People have calculated this, okay? And so what's going on here now? Remember, this is omega minus omega omega. So this is like a polarization that's proportional to E of omega, but with the intensity. But if it acquires an imaginary part, that's a polarization that's out of phase with the field that's driving it, and that means absorption. Okay, that we associate with absorption. And this, in fact, the imaginary part of this describes two-photon absorption in the same way that the imaginary part of chi1 describes one-photon absorption. Okay? And the question for you to think about, chi1, imaginary part of chi1 describes one-photon absorption. Imaginary part of chi3 describes two-photon absorption. What does the imaginary part of chi2 describe? Somebody can ask me that at the end if you haven't figured it out. Okay, but now let's look at a case. Let's look at a kind of a general expression for chi2 in this regime where I want to talk about crossing the gap and so on. So I have frequencies omega 1 and omega 2, and omega sigma here is just the sum of the frequencies. Okay? And it turns out you can write the expression for this. You could do the calculation with Adams and Blount, or you can do it with minimal coupling. Same result. You get an expression like this involving three terms that I've identified here. Okay? These two terms in the numerators here vanish if these frequencies are below the gap. Okay, so if my incident frequencies are below the gap, I don't have this. Just have this piece here. Okay? But if the frequencies are above the gap, I get the sigma 2 and the eta 2. Okay? And now, it turns out, though, that these numerators here, the sigma 2, the eta 2, and the chi bar 2, these are well behaved at all frequencies. Okay. So, let's look at a case where for my omega 1, I'm going to use omega, which is, say, above the gap. Okay? And for omega 2, I'm going to choose minus omega, right? Just the star of E of omega. Well, okay. That means that omega sigma goes to 0. This term here, well, that's 0 omega minus, that's just optical rectification. That's not a problem. But what's going on here? If omega sigma goes to 0, these terms seem to diverge. Okay? So what's the story? Well, let's look at them. Let's look at this term first, the sigma 2 term first. Okay? So that says I have a polarization that goes like this. But now we have to remember, well, really, J is dp dt. Okay? So what this really means is that I have a J that's going like the sigma 2 times E times E. And in the CW limit, I get a J that's independent of time, okay? That's proportional to E of omega, E of minus omega. That's a shift, that's called a shift current or a photovoltaic effect, okay? And what's happening here is that I've now got h bar omega greater than the gaps. I'm absorbing light, okay? I'm absorbing light at frequency omega, but in the DC regime, I'm driving a current, okay? And let's think about gallium arsenide. Well, let's look at, some of the bands in the valence bands here. Here's what the situation looks like. Most of the electrons are around the arsenic. That's the electronegative ion there. If I look at what's going on up here in the conduction band, well, some of the electrons have moved to the gallium. So if I absorb light here, somehow electrons have to get from being around the arsenic to being around the gallium. How are they going to do that? Well, it depends. Okay? But if you choose your electric field to be oscillating in this direction, it's light polarized along the 1-1-1 direction, then they're going to do that by moving from the arsenic to the gallium. That's a shift. Their position is shifting, and as the position is shifting, as light is being absorbed, okay, you will get this current. Okay, so that's the sigma term. Let's look at this term here. Okay? Now the eta term. Well, okay, same sort of story. Okay, right on. Again, we remember that J is dp dt. So this says that I'm getting a dj dt at eta, that's described by this eta, goes like e of the omegas. In the CW limit, I'm getting now a dj dt. That is proportional to the intensity. This is sometimes called an injection current or a circular photocurrent or a photogalvanic effect. Okay? And what's happening here is that, well, I can inject at a given frequency omega, I can get absorption here or absorption here. There'll be a probability. Okay, so the matrix element, there's a momentum matrix element going from V to C times the electric field. The probability for the transition is going to go like the square of that. But look what's going on here. I could have a couple pieces in here. I could have a Z component of the electric field. I could have an X component of the electric field. And these matrix elements are going to be different here than here. And so I can get interference between these two things, and I could get constructive interference over here and destructive interference over here. And that's precisely what this photogalvanic effect is. Depends very much on the crystal structure. Gallium nitride, for example, crystallizes in both the Wurtzite form and the zinc blende form. But eta 2 is 0 for the zinc blende form, but it's non-zero for the Wurtzite form. Okay? So depending on the crystal structure, you can get injection current or not. Okay? If you do get it, well, the direction of the current depends on the helicity of the beam. Okay? So you get a dj dt that will be positive or negative depending on whether you have right or left-handed circular polarization. This is the simplest case. It can get more complicated depending on which crystal face you're using. Okay. What about chi3? Well, what do you know? It's the same story. Okay? Same sort of story. Okay? You get the chi3 bar here, the sigma 3 and eta 3. If the sum of these frequencies goes to 0, there's going to be interesting things going on. Get omega sigma equal to 0. So that would say, well, I've got, 2 omega is crossing the gap, and, I can do that with the beam at 2 omega, or I can do it with 2 photons at omega. Okay. Let's just look at for time reasons, let's just look at the eta 3 term here. That's current injection. And now here's the story. Now I'm interfering a 2-photon amplitude, like this, with a 1-photon amplitude, the 2-photon amplitude at E of omega, the 1-photon amplitude at E of 2 omega, and I can get constructive interference over here and destructive interference over here. Or by changing the phase of the E of omega and E of 2 omega fields, I can get it, say, almost going just in one direction. People are investigating this actually to measure the carrier envelope phase in very short pulses. Okay, so there's a practical application for this. Okay. Now it's interesting. So here comes the light, and suddenly all the electrons are going in that direction. How did that happen? Well, they got the energy from the photons, but they didn't get the momentum from the photons. Photons have very low momentum, and indeed, in calculations like this, we completely neglect the momentum of the photons. Okay? They get the momentum from the lattice. The photons cause them to move in such a way that they get the momentum from the lattice. Okay? So the energy and the momentum come from different places. It's like when you get in your car. Well, maybe your car doesn't look like this, but maybe for some of the younger people it does. I don't know. You get in your car, you start up. Well, the energy comes from the gasoline, but the gasoline has no momentum. Right? The momentum comes from the road. Okay? Same sort of story. Okay? By playing around with these kind of interference effects, you can inject a spin polarized current, and you could also inject a pure spin current. where you call, spin ups go in one direction, spin down go in the other direction. Okay? But I have just a few minutes left, so what I'd like to let me finish up by talking about forbidden processes. Okay? So here I want to worry about the fact that the wavelength of light is not, or that the electric field is not uniform over a unit cell. Okay? There is some variation. Okay? Let's suppose I have a centrosymmetric medium, though. Chi2 is 0 because it's centrosymmetric. Okay? If I think about the long wavelength limit, I come in with light at omega, I should just get light at omega coming out. There should be no second harmonic generation. Okay? But in fact, yeah, you see some light coming out here, okay, at 2 omega. And what's going on is that you can get a polarization at 2 omega that's proportional to the electric field at omega and the derivative of the electric field at omega. Okay, so this has to do with the variation of the electric, but you see, because I introduced this, I got another component, right, to play with. So now I have a 4th rank tensor, and that's allowed, even if the material is centrosymmetric. Okay? We say it's forbidden because in the long wavelength limit, it vanishes. Okay? It's a little tricky, though, because despite the fact that the material is centrosymmetric, of course, I break inversion symmetry at the surface. Okay? Which means that in a small region near the surface, I can get allowed second harmonic generation. Okay? So in fact, I have to worry about allowed second harmonic generation at the surface and forbidden second harmonic generation. Yeah, it's forbidden, but it still happens, of course. I mean, in the bulk. Okay? And it's, yes?
But when you say the surface, how deep you can go in the surface to get the second harmonic?
In practice, you're going to get a field that often when this effect is large, you're also getting some absorption in the medium. So it's going to go about a fraction of a wavelength in. But the amount of forbidden SHG generated in about a wavelength is roughly comparable to the amount of allowed second harmonic generation done in a couple of angstroms. So the signal from the forbidden and allowed second harmonic generation here are comparable. Okay? And there's an interesting result, and that is, if all you can do is measure light out here, not inside the crystal, you don't have a photon detector in here, just measure light out here. Okay? If that's all you can do, you can prove that you cannot distinguish completely between, you can't pull out this delta 2 and this gamma. You can't separate these two effects. To fully separate them, you would have to be able to detect what's going on inside this crystal as well. Okay? So there are interesting subtleties with these forbidden processes. David, yeah?
The gamma is also spatial dispersion effects. Is that the same thing?
Yeah, that's right. You can see this. This is a spatial. Anything involving d by dks this is a nonlinear spatial dispersion effect. Okay. So that finishes my little list of things here. So I'm officially done. It's been great. I've had a lot of fun giving this talk. I hope. But I really like nonlinear optics. So if anybody wants to talk about nonlinear optics, I could do that for days and days and days. So if you have any questions, come and hunt me up. Okay. And I hope now that some of you who have worked on topological materials, okay, can start to do some optical alchemy now with topological materials as well. So thanks very much for your attention.
Maybe we have time for one or two very quick questions.
Right. So sorry. Yeah. So I have a question about that shift current.
Yes.
It's a confusing thing, that shift current. So the way you described it, it seemed like a transient current, right? Because
That's right.
So is it actually transient?
That's right. When the
You
pulse-
polarize. You cannot do that forever. You cannot move those charges
No,
forever. You
well,
have to stop.
if you put on a CW beam, of course, you can do it, not forever, but you could do it for a while, but then you start depleting the valence band, and, current's then going to, the carriers are eventually going to recombine and go back down and so on.
Right.
And people have done rough calculations of that, and the result is you'll get a kind of persistent shift current, but it'll be much weaker than the one you just calculate in the perturbation expansion.
So this, exciting and then going back does shift too, but you say
No.
they do not compensate.
No, yeah, but in general, what's going to happen long before it goes back, it's going to, you'll get scattering in the conduction band. It'll trickle
Sure.
down and position will get randomized. So when it goes back down, you'll get no shift. You only get shift when it's going up. But of course, if you start depleting the valence band, if you pump very hard and start depleting, then you can't kick as many carriers up anymore. And
So this real picture is sort of more helpful, right? You cannot be transferring those charges forever, so it has to stop at some point. Right.
Yeah.
But you say it's not stopping. You say it's just
It'll be the effect will get ameliorated, but it's always going to be there as long as you're pumping.
I guess that's one of those things I have to ask you later, right?
Okay.
Is your student question?
Oh, come on. Ageist.
We're all lifelong students, but any student question from the audience?
What's the answer to the riddle?
Oh, thank you. Yes. So the imaginary part of Chi2 talks about an interference between one photon absorption and two photon absorption. Okay? In the same way that you can get interference leading to these shift and injection currents, you can get a net interference between the amount of carriers you inject due to one and two photon absorption. And if they're both going on, you'll get an interference between those effects, and that's what the imaginary part of Chi2 describes.
So that means that it can be both sides.
Exactly.
Which advantages would you expect if you use topological materials to do optical alchemy? I didn't get it.
I came here to find out the answer to that. I'm hoping you're going to tell me.
Good. I think we should end on that
Okay.
outlook note.
Okay.
Let's thank John for a great.
Thanks.